I'm sorry, I cannot speak in Portuguese.
Maybe.
Italian.
Italian is somewhat similar.
Ok, Daniela. Ok, Daniela.
Ok. Bom dia a todos. É com muito prazer e uma honra para nós receber hoje o seminário da doutora Maria Antonieta Barucci, Antonella Barucci, como é conhecida. Eu vou fazer uma pequena introdução dela. Ela é pesquisadora sênior, classe excepcional do LESIA, do Observatório de Paris, em Paris-Meudon. Ela foi formada em matemática pela Universidade La Sapienza de Roma, na Itália, em 82, e com doutorado e depois habilitação em dirigir recherche na Universidade de Paris 7, em Paris, em 93. As linhas de pesquisa da professora é a exploração do sistema solar, da Terra e do espaço, tanto a partir de observações na Terra quanto do espaço, visando entender as propriedades físicas, dinâmicas, mineralógicas de pequenos corpos, estudos de processo de acreção e discos protoplanetário, estudo de gelos em objetos transneptunianos, caracterização de planetas anãos, origem e evolução do sistema solar como um todo, tá? E também, por outro lado, o desenvolvimento tecnológico, né, através de missões espaciais e o desenvolvimento de instrumentos para essas missões espaciais. Tanto é que ela teve participação como co-investigadora das missões, inúmeras missões, eu posso citar aqui a missão Cassini, a missão Smart One, Rosetta, Dawn, Bepi Colombo, DART, Hera, Osiris-Rex, a Hayabusa 2, das várias agências espaciais pelo mundo, tanto da NASA, ESA e JAXA, japonesa. Tá? Ela foi PI das propostas das missões Marco Polo e Marco Polo Rex, R, né? Selecionada no estudo de fase 1, né, pela ESA, né, e atualmente é PI do espectrógrafo MIRS da missão Mars Moon Exploration, tá, da Agência Espacial Japonesa, JAXA. Tem mais de 1.000 publicações, mais de 400 em revistas com revisão por pares e diversos livros, né, como posições. Vai ser presidente da divisão F, que é a divisão dos sistemas planetários de astrobiologia da União Astronômica Internacional, a partir de agosto, sendo vice-presidente agora, né? É coordenadora da participação da França no projeto da Comunidade Europeia, o NEO-ROX, como também foi coordenadora dos consórcios também da NeoShield e NeoShield 2, que foram outros projetos grandes sobre estudo de objetos em órbitas próximas da Terra. Foi membro do Comitê Europeu de Ciências Espaciais, em 2019 e 2020. É diretora do projeto sobre astrofísica e condições do surgimento da vida em desenvolvimento em 24 laboratórios na região da Ile-de-France. Foi vice-presidente do Conselho Nacional de Astrônomos e Físicos da França, no período de 2016 a 2018. Também foi diretora do LESIA, né, de 2001 a 2005. E, de 92 a 94, foi membro da equipe da definição da missão Rosetta. Tá? Recebeu inúmeros prêmios, tanto da NASA quanto da ESA, principalmente por suas contribuições a inúmeras missões espaciais, como eu citei antes. E, não, por último, também tem um asteroide 3485, chama Barucci, exatamente o asteroide dado em sua homenagem. Dear Antonella, it's my pleasure to invite you to present your seminar. And we thank you very much to have accepted to give this virtual seminar to us. The word is with you.
Okay, good morning, everybody. I'm so happy to be with you, even if we have this virtual seminar, because I'm very close to National Observatory in Rio de Janeiro. I spend a lot of time there, and I have a lot of good collaborators that we continue to work together. So it's really a big pleasure to be together with you, even if for this short time. So I will speak today about the Yabusa 2 mission. Yabusa 2 mission is a JAXA mission, and with the objective of this mission to understand the original material, the primitive material of our solar system. And in the last period, we had the two very important missions that are the sample return mission to primitive asteroids. So we have this mission, Yabusa 2, going to the asteroid Ryugu, that you know is an asteroid primitive of classified C-type. And this mission was launched in 2014, stayed 2 years around the asteroid, doing a lot of science, impact, delivering lander, and returned a sample to the Earth on December 2020. So these two missions were a sample return mission to bring back some pristine material of a primitive object. The other mission was the OSIRIS-REx that has been launched in 2016, always 2 years in orbit around Bennu, that is also a primitive asteroid, B-type, and with the objective to return to the Earth samples of this pristine material, but this will come back on 2023. So why this mission? This mission is to understand the origin of our solar system, but also to understand the condition for the emergence of life with some organic water. This object contains organic water, so it's very important for the origin and evolution of the life on Earth. Now, I know that you had already the discussion on the mission OSIRIS-REx, so today we can make the point on this mission because we had back the sample, but we have also an extension of the mission. So first of all this, why we need to study sample, why we want to study asteroid, the small body. If you look the formation of the nebula with dust and grain around the sun, we had the accretion of this material through collision, forming what we call a planetesimal, and then from planetesimals we formed the embryons and then planetoid. So the asteroid, the small body of solar system, are the planetesimals that formed the planets and formed our solar system. So they can contain very important information. But when you look at the distribution of these asteroids, you had a lot of these small bodies closer to the sun, more distant to the sun. And then we had the formation of planets, we had the migration planets. So we had the mixture with the migration of planets, mixture of material. And during the so-called heavy bombardment, we had also many collisions with the Earth of these asteroids. And in fact, when you look during what was called the late heavy bombardment, about 3.9 gigayears ago, we had the first sign of life coming on the Earth. So all this is discussed. There are many theories, but for the moment we think that the life on Earth could be bring from outside, from small bodies that changed the biosphere and bring some important material. In fact, if you look these objects can contain some very important material. So with the collision, they could have delivered to the Earth water, organic matter, and prebiotic molecular that were very important to give origin of the life. So this is the important reason why we need to study the small body in our solar system, but also why we need to study the sample return. The sample return is very important because we can observe from ground with a lot of telescope. We have a space mission there, but some analysis, the tile analysis, need very high precision. and we need to include to study trace of element at particle per billion level, and also isotopic ratio per particle per million, so of precision. And we need also very high spatial resolution of few microns or less, and all this require very heavy instrument like synchrotron or very sophisticated instrument that we cannot bring on space. We have on Earth, so the best is to bring some pristine inaltered material on Earth to do the analysis, to have all the details of this mission. So the Japanese are very famous, very good, because they did already one mission, Hayabusa 1. The mission was to the asteroid Itokawa, was a S-type evolved asteroid, and this mission was the first mission to a primitive asteroid. So the Japanese are very good. The mission was launched on December 3rd, 2014 from Japan. And so we had one swimby with the Earth. What means flyby, swimby from the Earth? We need the energy from the Earth from a gravitation to have to push the spacecraft up to the asteroid, and the asteroid was arriving to the asteroid in 2018. And so with the spacecraft was put, it was not in orbit to the asteroid, but was very close at 20 kilometers, and so we call it hovering. So it was just going close to the asteroid and following the asteroid in its orbit. So the mission is an incredible mission with the delivery of a lot of small rover called Minerva. The small rover like a shoes box, very small, but with several instruments on board. Then we have a larger rover called Mascot, made by DLR, the German agency, and CNES, French agency. And then we have also two samples, one in April, one later on. And these two samples was one on a surface, and the other one was after a collision, to study the material under the surface, to study the different material after the impact. So there was an impactor in 2019. There was a lot of exciting story with this mission. So at the end, we were very lucky. On December 5, the re-entry capsule was coming back to the Earth with sample inside. It was landed in Australia, in Woomera. And this is not the end of the mission. Why? Because for one side, we started to study this sample, but for the other side, the mission was so perfect. Everything was so good that they had still a lot of gasoline in the propulsion inside the spacecraft. So the Japanese the JAXA decided to continue the mission and have a flyby with the asteroid in 2026, have another swimby with the Earth in 2027, already to push to go more far, another one in 2028, up to arrive a very interesting object in 2031. This asteroid is called 1998 KY26. For a rendezvous, we will put in orbit around these objects. We start like a new mission. This is so just incredible. So here you have all the story of the Hayabusa 2, but here you have the extension of Hayabusa 2. So this spacecraft, the Japanese, as you know, are very good, are excellent in miniaturization. The spacecraft was only 590 kilograms, and the Mascot, the rover, was 10 kilograms, while the small Minerva, the small rovers, were less than half kilo each. So as you can see, here you have the spacecraft with the antenna, the solar panel, You have just with the human scale to see which are the dimension of the spacecraft. And so you have several instruments with the camera, infrared spectrometers, the LIDAR. This is a laser to measure the distance, and this horn here is the sample return that was used for the sampling. So these are the surprise what we had. This is the asteroid Ryugu. These were the first images of Ryugu when we were in orbit on June 30, and we were at the distance of 20 kilometers from the surface. So as you see, we have here the resolution. You can see the details up to 2 meters per pixel. So you can see on these objects the details so small. So this object has a diameter of 900 meters, and the albedo, as you know, is the reflection of the light, is 4.5%. So it's very, very dark objects. It's really primitive material, very, very dark. But as you can see, this shape is so-called top shape with the equatorial ridge. As you see, this is not really spherical, but you have an equatorial ridge, much more big. And why we have like this? Because this object is a rubble-pile, so it's an aggregate of material. As you can see from this simulation, when you have the sun can accelerate and can change the shape of the objects and change the rotation of the objects. So this is, so we call it the York effect, and so the York effect for aggregate of material can bring asteroids to have this shape, so-called top shape. And we have many objects that we start discovering with this strange shape. So, as we said before, we had the home position at 20 kilometers from the surface of the asteroids, and from this home position that was following the spacecraft, the asteroid, during its orbit, the spacecraft was changing the orbit in function of the scientific objective of delivery of the rovers or doing the sampling, etc. So, for example, this image is taken when the spacecraft was at 6 kilometers, and the resolution is much better, is half meter per pixel. So you have really details, you see craters, you see small stones up to 0.5 meter on the surface of Ryugu. But you had also a lot of boulders on the surface. You have dark and bright boulders. So all these are very important. And you see there are some boulders that are like just on the top of the surface. This is the demonstration that is really a rubble-pile. So an aggregate of material, an aggregator of small part of objects after collisions that reaggregate together and form this asteroid. So as you know, looking at the details of the surface, we can interpret and study all the evolution, the story of this body. So looking, for example, all the distribution of boulders, the distribution of craters, the dimension of the craters, we can give the age, we can give many details. So for example, you see here you have this equatorial ridge here in blue, then you have many craters on top of this, so this can give also the age of the surface. And then we have also many regolith that are moving, and we have crater with clusters or a chain of craters, and then we have craters that overlap different features. So after the formation, we have craters that overlap on these features. So looking the crater, comparing the crater with the other objects, seems that there was a multiple resurfacing event on top of these objects with an age that is estimated between 2 and 11 million years for this object. Then with the spectroscopy, we were able to study the composition. We know from observation from the ground. We had observation from the ground. We had observation with Daniela Lazzaro from the telescope SOAR and the ESO. We could observe from the ground Ryugu before the encounter. Here we have the observations. And here we have the observations obtained by the spacecraft by the NIRS instrument. So as you see, the spectrum is almost flat, but when you enlarge, you see features at 2.72. And this is a typical feature for phyllosilicate. So what means? It means that you had water on the surface of these objects that were able to create some phyllosilicate. So there was water in some time of the age of the asteroid. But as you see, the band is very small. And if you compare with all the meteorites we have on the Earth, no one meteorite really is similar on behavior. If we have, for example, Ivuna, that is warmed at 500 degrees, that could fit better these features. And here we have another CM2 that were shocked, so always at high temperature. And this means that Ryugu suffer a lot of high temperature close to the sun. So Ryugu is a rubble-pile object generated for impact fragments of an aqueous altered parent body that was later on partially dehydrated. So we study with all the techniques, we study with the statistical way, we try to see with all the variation, the surface of Ryugu, and we see that there are a part of the surface, especially the equatorial part or some area around the craters, that is much more pristine and primitive. So we had some variation connected to what we call space weathering. The space weathering is a phenomenon connected with the exposure of the cosmic ray or micrometeorite impact of a solar wind that can alter the surface of an asteroid. So this was why during the characterization of asteroids, we needed to check for surface more pristine, to have really the material that could be more pristine. So we tried to study the surface with all the data obtained by the spacecraft. And here, this is the work that was doing one of my students, Alice Pre, in Paris. And she were looking with different method, the band on the band at 2.72 micron, and try to study the variation with the different characterization. But the band was not changing a lot. In fact, if you see here, the variation is very small of the band. And she compared all this with the meteorite to try to compare and quantify the content of water on Ryugu. So there was a similar work done in laboratory to study the content of water on meteorites, to study the weight in percent of water content. And so we applied the same method on Ryugu and on meteorites. And here you have the value of the water. And we can say that this asteroid is very similar to the heated carbonaceous meteorite CM, but also could be similar to the Tagishi Lake. And this was with the different method. So this is the best we can do with the data obtained by the spacecraft, but of course all this will be confirmed with the sample, with the analysis of the sample, when we will have the sample in our lab. So we during the first period of the mission, we were interested in analyze all the surface to find the location that were safe for the landing of the rover, for the landing of the Minerva, and in particular to have the sampling. So if you say here, we have some features of some area that were characterized. So this the L08 was for the touchdown, the Mascot is MA9, and then the N6 was for Minerva 2, for example. Just to see, we had to study all the detail of surface, but also the composition to look for the most interesting part. So this was one of the best images obtained from the camera that was on board of the small rover Minerva. So as I told you, the Minerva was a rover that is like a box of shoes, very small. And this small camera that is like a camera that you can have in your portable phone was able to have this very high resolution. Look here, the resolution, here you have the size is 1 meter. The resolution was about 7 millimeters. And this is the best resolution we obtained on its surface. And so you can see really all the details of the surface of Ryugu, with the big boulder on the top, the shadow, and so on. And here is when he was jumping with the flash of the sun in front. And I think this is very amazing image of the surface of Ryugu. We say that we had also a rover that was called Mascot. This rover is a rover built by DLR, that is the German space agency, and by CNES, the French space agency. Mascot means a mobile asteroid surface scout. And as you see, this is the box where there were several instruments. So there was a camera, there was a spectrometer, and several different instruments. And here I like to compare this rover with the Philae, the one that we have on Rosetta mission. The Rosetta mission, as you know, was to the comet Churyumov-Gerasimenko, and was a ESA, European Space Agency mission, with the rover always built by CNES and DLR. But as you see, with evolution, we have the miniaturization of the instrument. So the rover for Rosetta was built a long time ago, was 100 kilos. It was built at the end of the last century, while the Mascot is only 10 kilos, and all is inside. So here is also to compare the Ryugu and the comet with the dimension, the different scale. So the rover, the Mascot, was delivered very close. The spacecraft was going very close to the surface for to have a easy delivery of the rover. As you know, this body is small with very low gravity, so it's complicated. It's not so easy. And here, what is very interesting, you have the shadow of the spacecraft on top of the asteroid. So here, here you have the spacecraft that you know is a 6 meter for 4 meters, and here is the Mascot when it was delivered, and here the shadow of the rover Mascot. So one of the most interesting results of the Mascot was this analysis on the surface, and here you had a resolution of centimeter. You see here, this is the dimension of 5 centimeter. And what was found, as you can see here, we found a lot of inclusion of the what is called calcium aluminum inclusion that we can find in meteorites, and that is very old, is the oldest matter that we can have on our solar system. So this is very intriguing, and we hope to have a very good analysis on the sample now. We have an impact on the surface of Ryugu. This impact was done with the projectile. The projectile was a Cooper projectile of 2.5 kilos, was delivered at 2 kilometers per second. And then we had a detonation of 4.5 kilogram, and it was at 500 meters of altitude. And this was like an explosion. As you can see, you can have all the material that is going out of the surface of the asteroid. So the interest was really to see the effect of this, of the give the density of the objects, but also to analyze inside the crater. So here you have the image with the variation of color of you can see inside, outside of the crater. And then we had the spectra inside, outside, that we could study the variation, as you can see here with the subsurface and the surface spectra, with all the different variation. And here you have also the spectra that was taken outside the crater after impact and inside the craters. And so all this could be interpreted like a surface where there is a space weathering and or radiative heating. But all this will be confirmed and will be with much more precision by the analysis of the sample. So we had two samples, one in a location and one near after the impact. And as you can see, this is the owner that took the sample. You had like a small projectile inside, like an aspirator, taking the sample inside. And then you had the several camera where you could put the different samples. So at the beginning, there was the possibility to have up to 3 samples, but we had only 2 samples. So there was 2 camera followed by the sample of the surface. And then when the sample was in the containers, these containers were pushed and put in the so-called re-entry capsule. The re-entry capsule is sealed in a very precise way to not have any contact, any stuff with the exterior. So here, this is very nice movie taken with one camera that was on the spacecraft. You can see the owner that is going down, and you see as before the shadow of the spacecraft. So this is an image taking an altitude of 21 meters when the spacecraft was rising at about 52 centimeters per second. This is the projectiles that were used for the impact. As we told, there was 2.5 Cooper projectiles, was at a velocity of 2 kilometers per second. Now there is a small museum at the JAXA in Japan, and the Space National Agency in, near Tokyo. And so we have all the detail of the missions, of the previous mission. So what happens? After we got the sample, it's so precious, so important that we have just to go back home. So we put the ion engine on in position on to come back to the Earth, and targeting the desert of Woomera that is in Australia. Is the more safe desert where we could deliver the re-entry capsule. So everything was so perfect that after delivery of the re-entry capsule, the spacecraft was moving with the velocity of 4.4 kilometers per second to continue for the extension mission, because everything was just so perfect. So this was decided just after the return of the re-entry capsule, to be sure that we had a good sample, and then the spacecraft was continuing for the next part of the mission. So all this is completely new. We are going to this new target was selected. This target is 1998 KY26, and this is to go there. We need 2 gravity assisted with the Earth to have the energy to reach the objects. And we will have also a flyby of another asteroid that is 2001 CC21. So why these 2 asteroids? The first one is a nice asteroid that is supposed to have a diameter of 700 meters with a rotational period of 5 hours, and is possibly a L-type object while the very interesting is the 1998 KY26, which is very small asteroid, 30 meters, and this very fast rotator, 10.7 minutes of rotation. So we will have the first information about fast rotator objects, and there is high probability that these objects is another primitive, so we can compare with the results obtained with the Hayabusa 2 and OSIRIS-REx mission. So these are the reason why was chosen this extended mission, to understand the spinning top shape objects, to observe rapid rotator objects, to study all these details on boulders and thermal properties. And as you know, all these objects are different one by other, so how we can better increase the statistics is very important. Each of them can give something completely different. So the spacecraft is going on. We will have to wait 2026 for the first data, but for the moment we add the sample. So this is on the top of this view graph. You can see the like stars that is entering in our atmosphere in the desert of Australia. So this was observed with different telescopes, and everything was prepared to look at, to search for the re-entry capsule. So there was telescope observing, there was helicopter there to look and see where the re-entry capsule was landing. There was a parachute to have the velocity. So as you can see here, you have very small re-entry capsule here with all the parachute that is out, and it was found. Why the desert of Australia? Because it's much easy to follow and to look for it. And when the re-entry capsule was detected, it was taken and put in a very safe way in the helicopter to be bring to JAXA for the curation facility. So to open the re-entry capsule, you have to be in a very clean space at the curation facility. Everything is inside these containers. As you can see, you have to put the hands here inside. You will not touch the material, but you will do this in a very clean way. Everything has to be hyper clean. So you see is the operation of the opening the capsule and remove all the material to look what is inside. And this was the big surprise that the space mission was done with success. We could have 0.1 gram of material. They got 5.4 grams, so it was wonderful results. We had the 2 containers full of materials, and here you see these black materials that was taken with different dimension of these small stones. But what was also, there was some gas. There was also detected some gas. This was detected as soon as there was open this re-entry capsule, and this was the first world sample return from deep space. This was a really exciting result. So why it's so important, why we want to study these objects, this primitive material? Because we have meteorites, and many people say, but you have meteorites come from asteroids. Why you have to go there to take sample? We need to take sample because the sample of these objects are much pristine than meteorites. Even if we have meteorites of 4.5 million years ago, the meteorites enter in atmosphere, they have impact. And particularly the meteorites that are the representative of the primitive material, they are very fragile, and so when they touch the soil of the earth, they can be completely fragmented. So it's very difficult to have the real representative of the original material. But anyway, from the results of the analysis of meteorites, we found some pre-solar grain. So with this analysis of this material, that for sure will be pristine, even more pristine than what we have, we will have information on the stellar nucleosynthesis, on the stellar condensation grain. We can have information on the study of an interstellar medium, with the study of mantle, the organics. We can have information about the protosolar nebula. So all the different accretion phases, process and time scale of our nebula, protosolar nebula. But then we can have also the formation of our planetary system. So we can have information about the inner solar system, the properties of planetesimals at the time of planetary formation. But as we say, during this accretion, we had the asteroid. We need to study the evolution of asteroid, because we have also between asteroid different story, different evolution with different alteration process, impact event, the regolith, all the history of the impact with the Earth, and up to the origin of life with the organics in these bodies. So I think with these small few grams of material, we can address a wide range of objectives that go very far away from the nucleosynthesis of our star formation up to the origin of the life on Earth. But the story is not finished. The story is not finished. We are waiting the analysis. We have this analysis, the material is in the lab, and this material will be classified, will be like we have in the library. You have to classify all the sample, to wait to give the first characterization, and then will be distributed around the world to analyze and to study all this in detail. All the laboratories that have sophisticated machine with nanosims, with very important, with the spectroscopy in laboratory, with high resolution Raman, and all different machine that will analyze all the sample. So we have to wait a little bit before we can have results on this sample. So I hope that in the near future we can discuss on the results we got from this mission. But I like to finish, before to finish this talk, to speak just 2 minutes about the MMX mission, because the Japanese are the best in the world on sample return. They were the first going to sample return of an asteroid with the Hayabusa 1. They did Hayabusa 2. Now they are working on MMX. MMX is Martian Moon Exploration Mission. So this mission will be launched in September 2024, will arrive to the Mars system in August 2025. We need 1 year more or less to reach Mars. It will stay for 3 years on orbit around the Mars system, and to come back to Earth in 2029. So the spacecraft will be in orbit around Phobos in the so-called quasi-stationary QSO, quasi-satellite orbits, and from there they will be in orbit around Mars and observe Phobos, Mars, and the other satellite Deimos. So Phobos will be studying all the details. We will have a very big characterization, and then we will have a lander. We will have a rover there, always done by CNES and LR, and we will have a sampling from the surface of Phobos coming back to the Earth, so in September 2029. So the spacecraft will land for several hours to collect a sample. At least the objective, the techniques will be different. In this case, the objective is to have at least 10 grams, and we will have 2 sampling, and we will have the sample with a small core that will go down at least of 2 centimeters on the surface of Phobos. So there will be several instruments. We are responsible at LESIA of MIRS, that is the Near-Infrared Spectrometer that will observe between 0.9 3.6 micron. Then we will have a MEGAN that is gamma ray neutron spectrometer from NASA. We will have Orochi and Tango that are two cameras at much wide and narrow resolution, the LIDAR, that light detection ranging, the circum-Martian dust monitor, and mass spectrum analyzer. So as we say, we have also a rover and the sample return. And so if you see here is the draw of the spacecraft with the exploration module. This is the exploration module that will be delivered on the surface of Phobos. So the objective of this mission will be a little bit different. The objective number one is to set the controversy on the origin of the Martian moon by close-up observation return sample of Phobos. This is really the best, the objective number one, because we don't know the origin of Phobos. So, but at the same time, it's also very important to study, constrain the processes of planetary formation and material transport in the region connecting the inner outer solar system, and also to reveal the evolution process of Martian system in the circum-Martian environment. And just to finish is why we don't know the origin of Phobos and Deimos. These two satellites of Mars have been studied from the Viking, from all the space mission to Mars. We have a lot of data, but all the data we have up to now, they tell us that the spectroscopy is very similar, the spectroscopy of Phobos and Deimos, very similar to the CD-type asteroids, so very similar to carbonaceous chondrite, more similar even to the D-type. And so this is going in favor of the captured origin of this satellite, like a captured asteroid. But in the same time, the orbit have a so low eccentricity, low inclination, that this dynamical orbit is much more in favor of the formation in situ by in-impact. So this is really what we want to know, and we hope that with this mission we will be able to understand the origin of these two satellites. I think I can stop here, and I'm ready for questions if you have any. Thanks for listening.
Thank you very much, Antonella, for this very interesting seminar on this very fantastic mission that it was the Hayabusa 2. That is not finished because we still have to wait for the analysis, and this will take a long time, and we will have information for many years to go to have really to know everything about it. I think I will just complement that you were speaking about the importance of this mission, sample mission. But there is another point that for observers on Earth, it is important, they are important to, let's say, calibrate the observation we make on here from Earth. So the missions, they can help us to know better from remote observation what really we are observing. So I think this is Simone. I think she raised her hand.
Yes, because as I was saying before, what is important on asteroids or small body in general is to study all them by statistical point of view, and this can be done only with the observation by ground. So this is something that we remind the very important. And what is the difficulty that we need to interpret all this observation by ground. So we give a classification, we give a taxonomy, we say this is the composition, but then to give the real interpretation is very difficult. So this is a way, in some sense, to check also the observation. So for few objects, different composition, we can have much more details And this will be a huge, huge contribution, what is called a ground truth, to interpret it, to better understand all the observation by the ground. So this is the first message. We need to continue to observation by ground to increase the data of all these objects. Because there are millions and millions of asteroids.
Too many to study. Simone, I think she raised her hand.
Yes,
Yeah.
yes. Thank you, Antonella. It was very nice. I don't know which part is more exciting in this mission. If the spacecraft, the collecting the material, bring it back, the analysis in the labs after. So it's very nice. And I think this calibration with the analysis in the laboratories in the Earth, so it's really fantastic. My question is just about this: how the laboratories have been chosen to analyze. You said that different laboratories around the Earth will analyze the samples. And is it part of the collaboration since the beginning, or will it have some kind of I don't know, affiliation?
Okay, I can explain.
Of
Yes.
course.
So the sample, generally, the objective is to keep half of the sample for the posterity. This was done with the sample from the moon, with the Apollo mission, because on the posterity you can develop new instrumentation. So you can reanalyze this sample that is kept in pristine, in a very safe place. You can start with the new instruments. So half would be for the posterity. Then the half you have is kept. At the beginning there are a discussion, if for example there is a collaboration with a different agency, you can have a discussion, say, okay, we put this instrument, but we would like to have 1 milligram of sample, but the majority is distributed like a call for telescope. You make a call. The call is international open call for the analysis, so there is a commission. The commission will analyze the different calls, the different proposals, and decide, okay, you need 0.1 milligram to do this analysis for this objective. They have this other objective. So it's like a proposal. You make a proposal, and so I know there are several laboratories in the world that will have the sample. Also France have the sample. There are a few laboratories in France they will analyze.
This is really great, really great. It's fantastic. It's such a great opportunity for different laboratories around the Earth. So nice, very nice. Thank you.
More question while the people are thinking. I have one other one. George?
Yeah, we have a question from YouTube. Felipe Monteiro is in YouTube for some reason.
Okay.
And the question is, both Ryugu and Bennu have very prominent reaches in the equator. How can these objects provide clues about the processes of binary formation? Could they be losing material? That's the question.
Okay. Not this one, but these objects are they can produce a binary. So I was showing with the small video this one before. I can show you again. When you have this aggregate of material and you form this rubble-pile, and you have the effect of YARP, you have this form that is called the top shape form, but then you can form also a binary. And this is the case, for example, of the target of the mission DART. So you can have many of these objects with the top shape that have a satellite. So they can produce a satellite in this way. So we don't have a satellite in the case of Ryugu, but we can have in some other object.
let me complement this question. We know that in the case of Bennu, it was observed some material coming off from Bennu. In the case of Ryugu, you have some observation of this kind, or you have not seen
Well,
any
no,
material around it?
there was any material seen coming out from Ryugu. With the resolution of the camera, or with the
Yeah.
resolution what we were able to see.
Okay. Another question or comment is on the extension of the mission. You will do only an orbit. What will be the observation of the asteroid, the target asteroid?
Yeah.
Because I don't think you will have a sample return of the extension mission.
The extension is no. You will not have the sample return.
Yeah.
You will have just one flyby with the first asteroid.
Yeah.
Then you have the different swim by with that to arrive to the last one in 2031, and that one they will be in orbit, but there will be no sample return. It's impossible.
Yeah, imagine. No, but it's really
like
remaining in orbit.
Yeah. It's a new mission with one flyby and one rendezvous, so it's like completely new mission.
Mm-hmm. Yeah.
So I have a question.
Yes.
The target, the small one, it's really, how small is it? The target for the
small one is very small. I think it was 30. I can tell you. Yeah. Is 30 meter estimated. We don't have the measure, the precise, so it's just with the magnitude and the albedo.
So I assume it's
very small.
Yeah, it's really small, and the taxonomy is from B to D, so probably don't have really.
Yeah, because I think it's just a visible spectrum that sometimes is similar to, could be primitive or could be like also M asteroids, because the slope is just color.
Right, so just color, right? So yeah, it's very interesting to think that they'll be able to get in orbit around this small thing is fantastic.
I don't know the details in which way they will be in orbit. I don't know if they will do the same like hovering or as they did on Ryugu, or in which way they will be in orbit. I don't know. They didn't give details on this yet. But you will observe it for some more time. It's not just a flyby. It will be really a rendezvous.
Regarding the mission to Mars and Phobos, these satellites are very dark, aren't they?
Yes.
So they are very simple.
It's like exactly D-type asteroid. The spectrum is very similar to asteroids.
Yeah, could be very interesting to compare these samples.
And the slope is red, and could be the band 2.7, but it's not sure. It's not so clear. So I think it would be really very important.
Yeah, for sure. Yeah, especially now that we have the samples from a C-type asteroid. It will be great, very great. It's fantastic what we can do with the technology nowadays can be done.
Yeah, I think this is the Japanese mission. If you think, sometimes I make the comparison between the I like to make comparison with the mission by NASA. They have a very huge experience. They are a huge mission. If you compare OSIRIS-REx and Hayabusa 2, is much more. It's really different. But the Japanese were able to, in a very small spacecraft, to have a rover, lander, collision, impact, sample return, all. And this is so fascinating from a technological point of view. This is just crazy.
I was preparing a seminar for my students on Mars exploration, and I was saying, "No, okay, you have tons of missions over there, active and not active, from ESA, from NASA, from China, from India, but we will have to wait until a Japanese mission will go to take a fragment, not from Mars, but from
Yeah, because the
its
idea
satellites."
is if it's an impact, if it's the result of impact with Mars, there will be material of Mars.
Yeah.
So it's a way to have some sample return from Mars for the first time. Even if it's a captured asteroid, you can have some dust from Mars.
Yeah, for sure.
So this will be
Fantastic.
the first time there will be sample from Phobos, from so far away object,
Yeah,
and probably some material from Mars.
great. Okay. I am very surprised about the 5.4 grams. I imagine the people of JAXA have been very, very happy.
Yeah, they were very excited. This was really a success. It was wonderful.
Yeah, because the Hayabusa was the first one, was very
Yeah.
small
Yeah.
samples.
So they were happy with 0.1 grams. They got
And 5.
50 times more. Now, with the mission MMX, they are supposed to have 10 grams, so they can have
100, 500, half a kilo.
half a kilo, yeah.
So they'll be using the same technology to get the samples from Hayabusa 2, I guess.
I don't understand.
You'll be using the same technology to
No,
get
it's different. It will be different technology.
They will land, no? On Phobos.
Yeah. They will land. They will stay a few hours, and there is a different mechanism. So they make a lot of advance in the technology.
That's fantastic. That's fantastic.
Okay, I think, Georgie, there are more questions from YouTube.
No, just that one.
Okay, so I think it's come time for thanks, Antonella, very much for this beautiful seminar, and we hope to hear very good news in a in a short time. And we hope to have you here in Rio de Janeiro, not only by video, very soon. You were supposed to be here last year in September for the CCA. Everything was closed. Now this year also, with everything closed, we will not.
But I hope the situation will improve in the world and we can continue as before, and to see, because the relation are very important. Exchange, direct exchange also.
Yeah. Video is okay, but nothing compares to in-person discussions. Okay, thank you very much, Antonella. It was a great pleasure to have you.
Thank you for the invitation. Thanks a lot.
Thank you. Thank you very much.
Bye.
Bye. Bye.
Bye. Thank you.
Thank you.